Black hole jets have become icons of cosmic violence and beauty, appearing in countless documentaries, science fiction films, and artistic renderings that attempt to capture their magnificent fury. These luminous streams of energy, stretching across distances that dwarf our entire galaxy, represent nature operating at scales and speeds that challenge human comprehension. Tonight, we journey through the complete story of these remarkable structures. Our story begins on a quiet night in 1918 at the Lick Observatory, perched high in the mountains east of San Jose, California. An astronomer named Heber Dost Curtis was carefully examining photographic plates of distant nebulae, those fuzzy patches of light that astronomers of his era were only beginning to understand. As he studied an image of a massive elliptical galaxy in the constellation Virgo, something unusual caught his attention. Extending from the bright central core of this galaxy, which we now call Messier 87, was a faint but unmistakable streak of light. Curtis described it in his notes as a curious straight ray, apparently connected to the nucleus by a thin line of matter. At the time, Curtis could not have understood what he was seeing. The concept of galaxies as separate island universes, distinct from our own Milky Way, was still being debated. The idea that matter could be ejected from celestial objects at nearly the speed of light would have seemed like pure fantasy. Yet there it was, captured on a glass photographic plate, a ghostly finger of light pointing outward from the heart of a distant stellar city. This single observation would eventually lead humanity to discover one of the most energetic and mysterious phenomena in the entire cosmos. The decades following Curtis's observation brought tremendous advances in our understanding of the universe. Edwin Hubble demonstrated conclusively that spiral nebulae were indeed separate galaxies, expanding our conception of cosmic geography beyond imagination. Astronomers began mapping the heavens with increasing precision, cataloguing thousands of galaxies and noting their various shapes and peculiarities. Yet the strange ray emanating from Messier 87 remained largely unexplained, a curiosity filed away in astronomical archives while other discoveries captured the scientific spotlight. Everything changed with the birth of radio astronomy. In 1932, a young engineer named Karl Jansky, working for Bell Telephone Laboratories, was investigating sources of static that interfered with transatlantic radio communications. Using a large rotating antenna he had constructed in a field in New Jersey, Jansky discovered that some of the interference was coming not from thunderstorms or human-made sources, but from the sky itself. Specifically, the strongest signals came from the direction of the centre of our Milky Way galaxy. Jansky had accidentally discovered that celestial objects could emit radio waves, opening an entirely new window onto the universe. The implications of Jansky's discovery took time to unfold. During the 1940s and 50s, astronomers began building dedicated radio telescopes, instruments designed specifically to detect and map the radio emissions from space. What they found was astonishing. Many of the brightest radio sources in the sky did not correspond to bright visible stars or even to the nearest galaxies. Instead, they seemed to come from extremely distant objects, sources so far away that their light had travelled for millions or even billions of years to reach Earth. One of the most powerful radio sources discovered during this era was given the designation Cygnus A, located in the constellation of the Swan. When astronomers finally managed to identify its optical counterpart in 1951, they found a peculiar galaxy that appeared to be two separate objects in collision. Even more remarkably, the radio emission did not come primarily from the galaxy itself, but from two enormous lobes positioned on either side of the visible galaxy, like giant ears extending hundreds of thousands of light years into intergalactic space, something within that distant galaxy was ejecting material outward with tremendous force, creating vast clouds of radio-emitting plasma far beyond the galaxy's visible boundaries. Throughout the 1950s and 60s, radio astronomers discovered more and more of these double-lobed radio sources. A pattern began to emerge. At the center of each source sat a galaxy, often appearing disturbed or unusual in some way. Extending outward from the galaxy's core were narrow channels or jets of material, which terminated in the bright radio lobes. The jets themselves were often difficult to detect, but their existence could be inferred from the geometry of the lobes and occasionally from faint optical or radio emissions along their length. The mystery deepened with the discovery of quasars in the early 1960s. These objects appeared as point-like sources of light, resembling stars in photographs, yet their spectra revealed enormous redshifts, indicating distances of billions of light-years. For objects so far away to appear so bright, they had to be emitting energy at rates that dwarfed entire galaxies. Some quasars were also powerful radio sources, and many showed evidence of jet-like structures similar to those seen in radio galaxies like Cygnus A. Whatever was powering these cosmic beacons had to be extraordinarily compact and extraordinarily energetic. The theoretical breakthrough came in 1963 when the mathematician Roy Kerr solved Einstein's equations of general relativity for a rotating black hole. This solution, known as the Kerr metric, described how space and time behaved around a massive spinning object, and it revealed something remarkable. A rotating black hole does not simply swallow everything that approaches it. Instead, it drags the fabric of space-time around with it, creating a region called the ergosphere, where nothing can remain stationary. Within this swirling maelstrom of warped space-time, energy could theoretically be extracted from the black hole's rotation itself. By the 1970s, astronomers had begun to piece together a coherent picture. The powerful radio sources, the mysterious quasars, and the jets seen extending from galactic cores were all manifestations of the same underlying phenomenon. At the center of certain galaxies lurked supermassive black holes, objects containing millions or even billions of times the mass of our Sun, compressed into regions smaller than our solar system. When matter fell toward these black holes, it formed swirling disks of superheated gas that released tremendous amounts of energy. And somehow, through processes that were not yet fully understood, some of this energy was channeled into narrow beams that shot outward at nearly the speed of light. The term active galactic nucleus, or AGN, was coined to describe these energetic galactic cores. Astronomers recognized that quasars, radio galaxies, and various other types of unusual galaxies were simply different views of the same basic phenomenon. When we happened to look directly down the barrel of a jet aimed toward Earth, we saw a blazar, an object of extreme brightness and rapid variability. When we viewed the system from the side, we saw a classical radio galaxy with its jets and lobes spread across the sky. The orientation of our line of sight, combined with the intrinsic properties of each system, determined what kind of active galaxy we observed. The 1980s and 90s brought increasingly detailed observations of black hole jets. The Very Large Array Radio Telescope in New Mexico, with its 27 dish antennas spread across the desert, could create images of unprecedented sharpness. Astronomers watched in amazement as they tracked bright knots of material moving along jets at apparent speeds faster than light, an optical illusion caused by the jet's motion toward us at nearly the speed of light. The Hubble Space Telescope, launched in 1990, revealed the optical glow of jets in exquisite detail, showing twisted filaments and shock waves within these cosmic rivers of energy. Perhaps no observation captured the public imagination more than the Hubble images of the jet in Messier 87. the same galaxy where Heber Curtis had noticed that curious straight ray more than 70 years earlier. The jet appeared as a luminous blue stream extending thousands of light-years from the galaxy's core, with bright knots along its length that seemed to mark regions of intense particle acceleration. At the base of the jet, hidden from direct view, lurked a black hole estimated to contain over 6 billion solar masses, one of the most massive black holes ever measured. As the 20th century drew to a close, astronomers had transformed black hole jets from unexplained curiosities into objects of intensive scientific study. They had mapped jets across the electromagnetic spectrum, from radio waves to gamma rays. They had measured jet speeds, compositions, and magnetic field structures. They had developed sophisticated computer simulations that could reproduce many observed jet properties. Yet fundamental questions remained. How exactly did black holes manage to accelerate matter to such extreme velocities? What determined whether a black hole would produce jets at all? How did jets maintain their narrow focus structure across distances of millions of light years? The 21st century would bring new tools and new discoveries that would begin to answer these questions. In April of 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole and its immediate surroundings, showing the shadow of the supermassive black hole in Messier 87 silhouetted against a ring of glowing gas. For the first time, humanity could see the very engine that powered those magnificent jets, the dark heart from which rivers of light emerged across the cosmos. From Curtis's curious straight ray to the Event Horizon Telescope's groundbreaking image, the story of black hole jet discovery spans more than a century of human curiosity and ingenuity. Each generation of astronomers built upon the work of those who came before, gradually assembling a picture of cosmic phenomena that would have seemed like pure magic to earlier ages. And yet, as we shall see in the chapters that follow, we have only begun to understand these remarkable structures. The jets themselves still hold secrets that challenge our deepest understanding of physics, secrets that patient observation and careful thought continue to reveal. To truly appreciate the magnificence of black hole jets, we must first understand the extraordinary objects that create them. Black holes represent one of nature's most extreme creations, places where matter has been compressed so completely that the very fabric of space and time becomes distorted beyond recognition. They are not merely dense objects or powerful gravitational fields. They are regions where the rules that govern our everyday experience break down entirely, where the concepts of distance and duration lose their familiar meanings. The story of black holes begins, as so many stories in modern physics do, with Albert Einstein. In 1915, Einstein completed his general theory of relativity, a revolutionary framework that described gravity not as a force pulling objects together, but as a curvature in the geometry of space-time itself. Massive objects, according to Einstein, create indentations in the fabric of the universe, and other objects follow curved paths through this warped geometry. The Earth orbits the Sun not because an invisible force pulls it inward, but because the Sun's mass has curved space-time in such a way that the Earth's natural straight-line motion through four-dimensional space-time appears as a curved orbit in three-dimensional space. Almost immediately after Einstein published his equations, the German physicist Karl Schwarzschild found an exact solution describing the space-time geometry around a perfectly spherical, non-rotating mass. Schwarzschild was serving in the German army during World War I, calculating artillery trajectories on the Russian front. Yet he found time to work through Einstein's complex mathematics. His solution revealed something remarkable and disturbing. If a mass were compressed within a certain critical radius, now called the Schwarzschild radius, the curvature of space-time would become so extreme that nothing, not even light, could escape from within that boundary. The Schwarzschild radius depends only on the mass of the object. For our Sun, it would be approximately 3 kilometers, meaning that if all the Sun's mass were somehow compressed into a sphere just 6 kilometers across, it would become a black hole. For Earth, the Schwarzschild radius is less than 1 centimeter. For a supermassive black hole containing 1 billion solar masses, the Schwarzschild radius extends to nearly 3 billion kilometers, larger than the orbit of Uranus around our Sun. These numbers hint at the tremendous range of scales over which black holes can exist. The boundary defined by the Schwarzschild radius is called the event horizon, a name that captures its profound physical significance. Events occurring within the event horizon can never be observed from outside because no signal, no light, no information of any kind can cross from inside to outside. The event horizon is not a physical surface that you could touch or stand upon. It is instead a mathematical boundary, a point of no return defined purely by the geometry of space-time. An astronaut falling through an event horizon might notice nothing unusual at the moment of crossing, yet from that instant onward, their future would contain only one destination, the singularity at the centre. The singularity represents the ultimate fate of matter that falls into a black hole. According to general relativity, all the mass within a black hole becomes compressed into a point of infinite density, a place where space-time curvature becomes infinite, and our current physical theories cease to make meaningful predictions. Most physicists believe that a complete theory of quantum gravity, which we do not yet possess, would reveal what actually happens at the singularity. Perhaps matter reaches some maximum density and rebounds, or perhaps it tunnels into another region of space-time, or perhaps something entirely beyond our current imagination occurs. For now, the singularity remains one of the deepest mysteries in physics. Black holes come in different sizes, and these size differences correspond to different formation mechanisms. Stellar mass black holes, typically containing between 3 and 100 solar masses, form when massive stars exhaust their nuclear fuel and collapse. Throughout its life, a star maintains a delicate balance between the outward pressure of nuclear fusion in its core and the inward pull of its own gravity. When fusion ceases, gravity wins decisively. For stars above a certain mass threshold, the collapse cannot be halted by any known force, and the stellar core implodes to form a black hole. The outer layers of the star may be blown away in a spectacular supernova explosion, but the core vanishes behind an event horizon, leaving behind a dark remnant that will endure for eons. At the opposite end of the mass spectrum lie the supermassive black holes, the true engines of the jets we are exploring tonight. These cosmic giants contain millions to billions of solar masses and reside at the centres of most, if not all, large galaxies. The supermassive black hole at the centre of our own Milky Way, known as Sagittarius, a star, contains approximately 4 million solar masses. The black hole in Messier 87, the source of the famous jet, contains over 6 billion solar masses. The most massive black holes ever discovered tip the scales at tens of billions of solar masses, containing more matter than many small galaxies. How supermassive black holes form remains an active area of research. They cannot have formed from the collapse of individual stars, because no star could ever grow large enough to leave behind such a massive remnant. Several theories compete to explain their origins. Perhaps they grew from smaller seed black holes that formed in the early universe, gradually accumulating mass over billions of years through the consumption of gas and the merger of smaller black holes. Perhaps they formed directly from the collapse of enormous primordial gas clouds in the young universe bypassing the stellar stage entirely. Perhaps both mechanisms contributed, with different black holes having different formation histories. Between stellar mass and supermassive black holes lies a mysterious intermediate category. Intermediate mass black holes, containing hundreds to hundreds of thousands of solar masses, have proven surprisingly difficult to detect with certainty. A few candidates have been identified in the centers of globular clusters and dwarf galaxies, but their existence and properties remain subjects of ongoing investigation. These intermediate objects might represent a crucial link in understanding how supermassive black holes grow, or they might form through entirely different processes. For the jets that concern us tonight, the most important black holes are the supermassive variety. Their enormous masses create correspondingly enormous gravitational fields, capable of accelerating matter to extreme velocities and heating gas to temperatures of millions of degrees. But mass alone does not determine whether a black hole will produce jets. Another crucial property is spin. The Kerr solution, which we mentioned earlier, describes rotating black holes, and most astrophysicists believe that real black holes do rotate, often quite rapidly. When matter falls into a black hole, it typically carries angular momentum, the rotational equivalent of linear momentum. This angular momentum is transferred to the black hole, causing it to spin faster. Over billions of years of consuming gas and merging with other black holes, supermassive black holes can accumulate tremendous amounts of angular momentum, spinning at rates approaching the theoretical maximum allowed by general relativity. A rotating black hole differs from a non-rotating one in several important ways. The event horizon becomes slightly flattened at the poles and bulges at the equator, though this distortion is not directly observable. More significantly, the rotating black hole drags spacetime around with it, creating a region called the ergosphere that lies outside the event horizon. Within the ergosphere, spacetime itself is moving, carried along by the black hole's rotation, like water swirling around a drain. Nothing within the ergosphere can remain stationary relative to distant observers, because doing so would require moving faster than light against the flow of spacetime. The ergosphere is crucial for understanding black hole jets because it provides a mechanism for extracting energy from the black hole's rotation. Through a process first described by Roger Penrose in 1969, particles entering the ergosphere can split in such a way that one fragment falls into the black hole, while the other escapes with more energy than the original particle possessed. The extra energy comes from the black hole's rotation, which decreases slightly with each such extraction. This Penrose process, while important conceptually, is probably not the primary mechanism powering astrophysical jets. However, it demonstrates that rotating black holes are not simply cosmic vacuum cleaners that only consume energy. They can also give energy back to their surroundings under the right circumstances. The environment immediately surrounding a supermassive black hole plays an equally important role in jet formation. Black holes in isolation, drifting through empty intergalactic space, produce no jets because they have no fuel to work with. Jets require a steady supply of matter falling toward the black hole, matter that can be heated, accelerated, and channeled into those narrow beams of energy we observe. This infalling matter comes from the black hole's accretion disk, a swirling structure that deserves detailed examination in its own right. When gas approaches a supermassive black hole, it rarely falls directly inward. Instead, because the gas typically possesses some angular momentum, it settles into a rotating disk that orbits the black hole, much as planets orbit a star. This accretion disk can extend from just outside the event horizon to distances of light days or even light weeks from the black hole. The inner regions of the disk orbit faster than the outer regions, and this differential rotation creates friction between adjacent layers of gas. The friction heats the gas to extreme temperatures and causes it to gradually spiral inward, losing angular momentum and falling ever closer to the black hole. The temperatures in an accretion disk around a supermassive black hole can reach millions of degrees in the innermost regions, hot enough to emit copious X-rays and ultraviolet radiation. This radiation is what makes active galactic nuclei so luminous, outshining all the hundreds of billions of stars in their host galaxies combined. The total power output of a bright quasar can exceed 10 trillion times the luminosity of our Sun, all generated from a region smaller than our solar system. No other known process in the universe can convert matter into energy with such efficiency, yet the accretion disk alone does not explain the jets. Plenty of black holes possess accretion disks without producing significant jets, while others launch jets of tremendous power. The missing ingredient appears to be magnetic fields. Strong, organized magnetic fields threading through the accretion disk and the ergosphere can tap into the rotational energy of both the disk and the black hole itself, channeling that energy into the narrow columns of accelerated plasma that we observe as jets. The precise details of how this magnetic extraction works will occupy us in a later chapter, but for now, we can appreciate that jets require a specific combination of ingredients: a supermassive black hole, preferably rapidly rotating, surrounded by a substantial accretion disk, all threaded by strong and well-organized magnetic fields. The black holes that power jets are not passive objects waiting to be fed. They actively influence their surroundings, shaping the flow of gas and the structure of magnetic fields in ways that either promote or suppress jet formation. The interplay between black hole, accretion disk, and magnetic field is complex and dynamic, varying over timescales from hours to millions of years. Understanding this interplay has been one of the great challenges of modern astrophysics, requiring observations across the electromagnetic spectrum, sophisticated computer simulations, and deep theoretical insights. As we prepare to examine the anatomy of jets themselves, we should pause to appreciate the remarkable nature of the engines that create them. Black holes are objects that should not exist according to everyday intuition, places where space and time behave in ways that defy common sense. Yet they do exist, scattered throughout the universe in their billions, and some of them have been producing jets for longer than Earth has existed. The same physical laws that govern falling apples and orbiting planets, when pushed to their extremes, give rise to phenomena of almost incomprehensible power and beauty. The jets are messengers from these extreme environments, carrying information about physics at its most fundamental across the vast distances of intergalactic space. Now that we understand the engines that power black hole jets, let us examine the jets themselves in detail. These structures, extending from the immediate vicinity of supermassive black holes to distances of millions of light years, possess a complex anatomy that astronomers have spent decades mapping and characterizing. From the base near the black hole to the enormous lobes where jets finally dissipate their energy, each component tells us something about the physics of these extraordinary phenomena. Our anatomical tour begins at the very heart of the system, in the region closest to the black hole where the jet first forms. This innermost zone, sometimes called the jet launching region, lies within just a few Schwarzschild radii of the event horizon. Here, the gravitational field is so intense that space-time itself is severely warped, and matter moves at significant fractions of the speed of light simply from orbital motion around the black hole. The accretion disk in this region is geometrically thin but extraordinarily hot, radiating fierce X-rays and ultraviolet light. Magnetic field lines thread through this inner accretion disk, anchored in the conducting plasma and dragged along by its rotation. Near the black hole, these field lines become twisted and wound up by the differential rotation of the disk, building up magnetic pressure that eventually finds release in the vertical direction, perpendicular to the disk plane. The magnetic field forms a funnel-shaped structure above and below the disk, with field lines converging toward the rotation axis of the black hole. Plasma from the inner disk is loaded onto these field lines and accelerated outward, beginning its long journey as part of the jet. The exact mechanism by which plasma is accelerated in this launching region remains a subject of active research and debate. Several processes likely contribute. Magnetic pressure gradients push plasma outward along the field lines. Centrifugal forces fling material away from the rotating field structure. Heating from magnetic reconnection events adds thermal energy that helps drive expansion. And the Blandford-Znajek mechanism, which we will explore in detail later, extracts rotational energy directly from the spinning black hole and converts it into outward-flowing electromagnetic energy. The relative importance of these different processes probably varies from jet to jet and may even vary within a single jet over time. Moving outward from the launching region, we encounter the acceleration and collimation zone. Over distances ranging from tens to thousands of Schwarzschild radii, the jet transitions from a relatively wide, slow-moving flow to a narrow, fast-moving beam. This transition is crucial for creating the highly focused jets we observe, and it appears to be accomplished primarily through the action of magnetic fields. The magnetic field geometry in this zone resembles a helix or corkscrew, with field lines wrapping around the jet axis while also extending along it. This helical structure creates a magnetic pressure that squeezes the jet from the sides, confining the plasma into a narrow column. At the same time, the tension in the field lines pulls the plasma forward, continuing to accelerate it toward higher velocities. The combination of confinement and acceleration transforms the initial outflow into a focused beam moving at a substantial fraction of light speed. Observations of nearby jets with very long baseline interferometry, a technique that combines radio telescopes across different continents to achieve extraordinary angular resolution, have begun to reveal the structure of this acceleration and collimation zone. In Messier 87, for instance, astronomers have traced the jet from scales of just a few light days from the black hole out to distances of several light years, watching as the jet gradually narrows and brightens. The opening angle of the jet, the angle it makes as it spreads outward, decreases from relatively wide near the black hole to very narrow further out, exactly as predicted by magnetic collimation models. Beyond the acceleration zone, the jet enters what might be called its mature phase, where it has achieved most of its final velocity and maintains a relatively stable structure. In this region, the jet appears as a narrow luminous column, often showing a series of bright knots or blobs along its length. These knots represent regions of enhanced emission, places where the jet plasma is radiating more intensely than its surroundings. The origin of these knots has been debated for decades, with several possible explanations proposed. One possibility is that the knots represent shock waves within the jet, places where faster-moving material has caught up with slower-moving material ahead of it. When jet material passes through a shock, it is compressed and heated, causing electrons to radiate more intensely. The shock might form when the central engine ejects a particularly energetic burst of material, or when instabilities within the jet cause variations in flow speed. Observations of knot motion in several jets support this interpretation, showing bright features that appear to move outward along the jet at apparent speeds, sometimes exceeding the speed of light. These superluminal motions, as they are called, do not actually represent faster than light travel. They are instead an optical illusion created when material moves toward us at nearly the speed of light. Because the material is chasing its own light, emission from different positions along its path arrives at Earth with compressed time intervals, making the motion appear faster than it actually is. The detection of superluminal motion in a jet provides strong evidence that the jet material is moving at relativistic speeds, typically 90% or more of light speed. Another explanation for jet knots involves instabilities in the jet structure. As the jet propagates through the surrounding medium, it can develop wave-like disturbances that grow over time, causing the jet to wiggle or pinch at certain locations. These instabilities might be triggered by interactions with the external medium, by variations in the jet launching process, or by inherent properties of the magnetized plasma flow. Where the instabilities cause the jet to compress, enhanced emission would result, creating the appearance of bright knots. Still another possibility is that some knots represent places where the jet is interacting with obstacles in its path. Clouds of gas, stars, or other material that wander into the jet's path would be shocked and heated, creating localized regions of enhanced emission. Evidence for such interactions has been found in some jets, where knots appear to be stationary rather than moving outward with the flow. The mature jet maintains its structure through a delicate balance of forces. Magnetic pressure and tension continue to confine the plasma, preventing it from spreading out too rapidly. The forward momentum of the relativistic flow keeps the jet moving outward, despite any resistance from the surrounding medium. Internal pressure from the hot plasma provides additional support against external compression, and the overall geometry of the magnetic field, still helical but now stretched out along the jet length, provides a kind of electromagnetic backbone that maintains coherence over vast distances. As we follow the jet outward, we eventually reach the region where it begins to interact significantly with its surroundings. For jets propagating through the interstellar medium of their host galaxy, this interaction begins relatively close to the nucleus, perhaps a few thousand light years from the black hole. For jets that have escaped their host galaxy and are ploughing through the intergalactic medium, the interaction zone may lie hundreds of thousands or even millions of light years from the central engine. The interaction between jet and external medium produces some of the most spectacular structures in the universe. Where the fast-moving jet material collides with the relatively stationary external gas, powerful shock waves form. The jet material is abruptly decelerated, its organized forward motion converted into random thermal motion and turbulence. The external gas is pushed aside and heated, creating a cocoon of hot, shocked material surrounding the jet. The kinetic energy that the jet carried from the black hole is finally deposited into the intergalactic medium, heating and stirring the gas on scales of hundreds of thousands of light years. The terminal shock where the jet finally stops is called the hotspot. In radio images, hotspots appear as bright, compact regions at the outer edges of the radio lobes, marking the current working surface where jet energy is being deposited. The emission from hotspots comes primarily from electrons that have been accelerated to extreme energies by the shock, electrons that spiral around magnetic field lines and emit synchrotron radiation across the electromagnetic spectrum. Hotspot emission can be detected from radio wavelengths through optical and sometimes even into X-rays, testimony to the extreme particle acceleration occurring at these cosmic shock fronts. Behind the hotspot, the spent jet material accumulates to form the radio lobe. Lobes are vast, diffuse structures filled with magnetized plasma that has passed through the terminal shock and is now flowing back around the jet in a kind of cosmic backwash. The plasma in the lobes is still hot and still contains energetic particles, but it is no longer organized into a coherent flow. Instead, it forms a turbulent, churning cloud that gradually expands and fades as the energetic particles lose their energy through radiation, and as the magnetic field weakens through expansion. Radiolobes can be enormous, dwarfing their host galaxies and extending to distances of millions of light-years from the central black hole. The largest known radio source, a giant radio galaxy called Alcyoneus discovered in 2022, has lobes spanning approximately 16 million light-years from tip to tip, making it the largest known structure in the universe created by a single galaxy. The energy contained in such lobes is staggering, equivalent to millions of supernova explosions, all ultimately derived from matter falling into the central black hole. The morphology of radiolobes varies considerably from source to source. Some jets produce lobes that are edge-brightened, with the hotspots clearly visible at the outer boundaries. These are classified as Phaneroff-Rayleigh Type II sources, named after the astronomers who first described the classification scheme in 1974. Other jets produce lobes that are center-brightened, with the emission concentrated closer to the host galaxy and no clear hotspots. These are Phaneroff-Rayleigh Type I sources. The distinction between these two classes appears to be related to jet power, with more powerful jets producing Type II morphologies and less powerful jets producing Type I morphologies. The reason for this morphological difference involves how the jet interacts with its surrounding environment as it propagates outward from the central black hole. In powerful Phaneroff-Rayleigh Type II sources, the jet maintains its coherent supersonic flow all the way to the outer reaches of the lobe. The jet material remains fast and focused, punching through the intergalactic medium like a cosmic battering ram until it finally encounters enough resistance to form a strong terminal shock. This shock creates the bright hotspot we observe at the lobe's edge, where particles are freshly accelerated to their highest energies. In contrast, the less powerful jets of Phaneroff-Rayleigh Type I sources appear to decelerate and disrupt much closer to the host galaxy. These jets lose their organized structure through interactions with the surrounding gas, through internal instabilities, or through some combination of both processes. Rather than maintaining a narrow, focused beam that terminates in a distant hotspot, the Type I jet spreads out and merges gradually with its lobe, depositing its energy over a broader region. The result is a more diffuse, center-brightened structure without the dramatic edge features seen in Type II sources. The boundary between these two classes occurs at a radioluminosity of roughly 10 to the 25th watts per hertz at a frequency of 178 megahertz, though this division is not perfectly sharp. Some sources show intermediate properties, and the morphology can also depend on the density and distribution of gas in the surrounding environment. A jet of moderate power might appear as Type II if it propagates through a low-density medium that offers little resistance, or as Type I if it must fight through a denser environment that disrupts its flow more effectively. Beyond the radiolobes, some sources show even larger structures called relics or ghosts. These are regions of faint radio emission that mark the locations of former lobes, places where jet activity occurred in the past but has since ceased. As the central engine turns off or reduces its power output, the lobes stop receiving fresh energy from the jet. The energetic particles within them gradually lose their energy through radiation and through collisions with low-energy photons, causing the emission to fade. The magnetic field also weakens as the lobe expands and as magnetic reconnection converts organized field energy into heat. Over millions of years, the once bright lobe dims to a ghostly remnant. a fossil record of past jet activity. The detection of these relic lobes tells us that jet activity is episodic rather than continuous. Black holes do not simply turn on their jets and leave them running forever. Instead, the jets turn on and off repeatedly over the lifetime of the galaxy, with active episodes lasting perhaps tens of millions of years, separated by quiet periods of similar or longer duration. The reasons for this episodic behavior are not fully understood, but they probably involve variations in the fuel supply reaching the black hole. When abundant gas is available, the accretion rate is high and powerful jets can be launched. When the gas supply diminishes, the accretion rate drops and the jets weaken or cease entirely. As we complete our anatomical survey of black hole jets, we should appreciate the remarkable range of scales involved. The jet launching region, where plasma is first accelerated away from the black hole, spans distances comparable to our solar system, perhaps a few light hours or light days across. The acceleration and collimation zone extends over light years to tens of light years. The mature jet can maintain its structure over thousands to hundreds of thousands of light years, and the radio lobes, where the jet's energy is finally deposited, can span millions of light years from end to end. This hierarchy of scales, covering more than 10 orders of magnitude in distance, is all connected by the continuous flow of energy and matter from the compact central engine to the vast outer structures. The anatomy of a black hole jet reflects the physics operating at each location along its length. Near the black hole, general relativity and magnetohydrodynamics govern the launching process. In the acceleration zone, magnetic forces dominate the dynamics. In the mature jet, relativistic fluid mechanics and plasma instabilities shape the flow. At the terminal shock and in the lobes, particle acceleration and radiative processes determine what we observe. Understanding jets requires mastering physics across this entire range, from the curved space-time near the event horizon to the dilute plasmas of intergalactic space. Having surveyed the anatomy of black hole jets, we now turn to one of the most profound questions in astrophysics. How do these remarkable structures actually form? What physical processes can extract energy from a black hole and its surroundings, accelerate matter to nearly the speed of light, and focus that matter into narrow beams that maintain their coherence across millions of light years? The answers involve some of the most elegant and powerful ideas in theoretical physics. Ideas that connect the warping of spacetime to the behavior of magnetic fields in ways that even Einstein might have found surprising. The fundamental challenge of jet formation can be stated simply. A black hole is, by definition, an object from which nothing can escape. Yet jets appear to originate from the immediate vicinity of black holes, carrying away enormous amounts of energy. How can energy escape from something that is supposed to trap everything? The resolution of this apparent paradox lies in recognizing that jets do not actually emerge from inside the event horizon. Instead, they are powered by processes occurring just outside the horizon, in the accretion disk and in the ergosphere of a rotating black hole. The most widely accepted mechanism for powering the most energetic jets is called the Blandford-Znajek process, named after Roger Blandford and Roman Znajek, who first described it in a landmark paper published in 1977. This mechanism extracts energy directly from the rotation of the black hole itself, using magnetic fields as the intermediary. To understand how it works, we must first appreciate how magnetic fields behave in the extreme environment near a spinning black hole. Magnetic field lines in the classical picture are continuous curves that never begin or end. They form closed loops, or they extend to infinity, or they wrap around in complex patterns, but they do not have endpoints where they simply stop. When magnetic field lines thread through a conducting medium, Like the plasma of an accretion disk, they become anchored to that medium and are dragged along with its motion. The plasma and the magnetic field become coupled together, each influencing the behavior of the other. Near a rotating black hole, the ergosphere creates a region where space-time itself is dragged around by the black hole's spin. Any magnetic field lines that pass through the ergosphere are also dragged around, forced to rotate by the swirling space-time, even if they are not directly attached to any matter. This rotation of the magnetic field lines is the key to the Blandford-Snudek process. A rotating magnetic field is not a static structure. It is a dynamic configuration that carries energy and angular momentum. Just as a spinning flywheel stores rotational energy that can be extracted to do useful work, a rotating magnetic field stores electromagnetic energy that can be extracted and converted into other forms. The Blandford-Snudek process accomplishes this extraction by allowing the rotating magnetic field to do work on charged particles in the magnetosphere surrounding the black hole. The magnetosphere is a region of low-density plasma and strong magnetic field that exists above and below the accretion disk, extending along the rotation axis of the black hole. In this region, the magnetic field is so strong that it dominates the dynamics, with the sparse plasma forced to follow the field lines rather than moving independently. The rotating magnetic field accelerates charged particles outward along the rotation axis, flinging them away from the black hole at velocities approaching the speed of light. The energy for this acceleration comes ultimately from the rotational energy of the black hole. As the magnetic field extracts energy and angular momentum, the black hole spins down slightly, rotating a tiny bit slower than before. Over billions of years, a continuously active jet could theoretically extract a significant fraction of the black hole's rotational energy, though in practice, the process is limited by the availability of magnetic flux and the stability of the configuration. The power output of the Blandford-Snudek process depends on several factors: the mass of the black hole, its spin rate, and the strength of the magnetic field threading the horizon. For a maximally spinning black hole with a strong magnetic field, the power can be enormous, easily exceeding the luminosity of the accretion disk and rivaling the total energy output of a quasar. This makes the Blandford-Snudek process the leading candidate for explaining the most powerful jets observed in nature. However, the Blandford-Snudek process is not the only mechanism that can contribute to jet formation. The accretion disk itself can also launch outflows through a process called the Blandford Payne mechanism, described by Roger Blandford and David Payne in 1982. This mechanism does not require a rotating black hole. Instead, it relies on magnetic field lines that are anchored in the rotating accretion disk and extend outward at an angle to the disk surface. When the angle between the magnetic field lines and the disk surface exceeds 30 degrees, a remarkable thing happens. Plasma in the disk experiences a centrifugal force that flings it outward along the field lines, like water drops flying off a spinning umbrella. The magnetic field acts as a kind of rigid wire along which the plasma can slide, and the rotation of the disk provides the centrifugal force that drives the outward motion. As the plasma moves outward, it gains speed, eventually reaching velocities that can be a significant fraction of the speed of light. The Blandford Payne mechanism can operate even around non-rotating black holes, as long as the accretion disk is present and threaded by appropriately oriented magnetic field lines. It probably contributes to the mass loading of jets, providing the actual particles that carry the jet's kinetic energy. The Blandford-Snudek process, by contrast, is more efficient at producing electromagnetic energy flux, the Poynting flux that dominates the energy content of jets near their base. In reality, both mechanisms probably operate simultaneously in most jet-producing systems, with their relative contributions depending on the specific properties of the black hole and its accretion disk. The Blandford-Zinajek process may dominate the energy extraction, while the Blandford-Payne process provides the mass that eventually becomes visible as the jet plasma. The two mechanisms work together, drawing on different energy reservoirs but combining to produce the powerful particle-laden jets we observe. Beyond these two primary mechanisms, other processes can contribute to jet acceleration and collimation. Radiation pressure from the intense luminosity of the accretion disk can push material outward, particularly along the rotation axis where the disk presents its smallest cross-section. Thermal pressure from the extremely hot gas in the innermost accretion regions can drive winds that may be focused into jet-like structures by magnetic fields, and magnetic reconnection events, where tangled magnetic field lines suddenly rearrange themselves and release stored energy, can provide impulsive acceleration to parcels of plasma within the jet. The collimation of jets, the process by which they are focused into narrow beams, deserves special attention. The initial outflow from the black hole vicinity is not particularly well collimated. It emerges over a fairly wide angle, more like a broad wind than a narrow jet. The transformation into a tightly focused beam occurs over distances of hundreds to thousands of gravitational radii from the black hole, through the action of magnetic forces. The key to magnetic collimation is the hoop stress exerted by toroidal magnetic field components, the parts of the magnetic field that wrap around the jet axis like rings on a barrel. These toroidal components are generated naturally as the initial poloidal field, the component parallel to the jet axis, is wound up by the rotation of the black hole and accretion disk. The toroidal field creates an inward-directed magnetic pressure that squeezes the jet from the sides, confining it to a narrow column. At the same time, the tension in the poloidal field lines provides a kind of backbone that keeps the jet from pinching off entirely. The balance between toroidal pressure, pushing inward, and poloidal tension resisting compression determines the equilibrium diameter of the jet. As the jet propagates outward and the magnetic field strength decreases, this balance shifts, and the jet may gradually expand. But the initial collimation achieved near the black hole is maintained over vast distances, allowing jets to remain focused beams across millions of light years. Computer simulations have been invaluable in testing and refining our understanding of jet formation physics. Modern simulations can model the behavior of magnetized plasma in the curved spacetime near a rotating black hole, following the flow from the accretion disk through the jet launching region and out into the propagating jet. These simulations have confirmed the basic picture of magnetic jet launching and collimation, while also revealing complexities that analytical theory alone could not capture. One important finding from simulations is that jet formation is inherently time variable. The magnetic field configuration near the black hole is not static but constantly evolving, with magnetic flux accumulating, reconnecting, and being ejected in a quasi-periodic fashion. This variability at the jet base propagates outward as fluctuations in jet power and structure, potentially explaining some of the knots and brightness variations observed in real jets. Simulations have also revealed the importance of the magnetic flux accumulated on the black hole. When enough magnetic flux builds up on the horizon, it can actually impede the accretion of matter, creating a magnetically arrested disk state where the magnetic field is strong enough to partially balance gravity. Jets produced in this magnetically arrested state tend to be particularly powerful and well collimated, suggesting that the most impressive jets in nature may arise from systems that have achieved this special configuration. The physics of jet formation connects some of the deepest ideas in theoretical physics. General relativity, which describes the curved space-time near black holes. Magnetohydrodynamics, which describes the behavior of conducting fluids in magnetic fields. And plasma physics, which describes the collective behavior of charged particles. Bringing these disciplines together to understand jets has been one of the great intellectual achievements of modern astrophysics, though significant mysteries remain. We still do not fully understand what determines whether a given black hole will produce jets at all. Many supermassive black holes with substantial accretion disks show no evidence of jet activity, while others launch jets of tremendous power. The difference may lie in the magnetic flux available to the black hole, in the spin rate of the black hole, in the properties of the accretion flow, or in some combination of all these factors. Identifying the key parameters that control jet production remains an active area of research. We also do not fully understand the composition of jets. Are they primarily composed of electrons and positrons, the antimatter counterparts of electrons? Or do they contain a significant fraction of protons and heavier ions? The answer has important implications for jet energetics and for the ability of jets to influence their surroundings. Observational constraints on jet composition have been difficult to obtain, and different lines of evidence sometimes point in different directions. Despite these remaining puzzles, the basic framework for understanding jet formation is now well established. Rotating black holes, threaded by strong magnetic fields and fed by accretion disks, can launch powerful outflows that are accelerated and collimated by electromagnetic forces. The energy for these outflows comes from the gravitational potential energy of accreting matter and from the rotational energy of the black hole itself. Nature has found a way to tap into these enormous energy reservoirs and channel the extracted energy into focused beams that can cross intergalactic distances. Among all the black hole jets that astronomers have studied, none has achieved greater fame than the jet emanating from the supermassive black hole at the centre of Messier 87. This giant elliptical galaxy, located approximately 55 million light-years from Earth in the constellation Virgo, hosts one of the most massive black holes ever measured and produces a jet that has been observed and studied for over a century. The story of the Messier 87 jet is in many ways the story of our growing understanding of black hole jets in general. Messier 87, often abbreviated simply as M87, was first catalogued by the French astronomer Charles Messier in 1781. Messier was primarily interested in comets, and he compiled his famous catalogue of fuzzy objects partly to avoid confusing them with the comets he sought. The 87th entry in his catalogue was a large round nebula in Virgo that showed no structure in his small telescope. Messier could not have known that this fuzzy blob was actually a galaxy containing trillions of stars, located far beyond the boundaries of our own Milky Way. The true nature of M87 began to emerge in the early 20th century, as larger telescopes revealed more detail. The galaxy appeared as an enormous elliptical mass of stars, one of the largest galaxies in the nearby universe. It sits at the centre of the Virgo cluster, a collection of over 1,000 galaxies that represents the nearest large galaxy cluster to our own local group. The dominant position of M87 within this cluster suggests a long history of growth through the consumption of smaller galaxies, a process that may have contributed to the enormous mass of its central black hole. The discovery of the jet in 1918 by Heber Curtis, which we discussed in our opening chapter, marked the beginning of M87's special status in the study of active galaxies. Curtis described the jet as a curious straight ray connected to the nucleus by a thin line of matter, a description that remains apt today. The jet extends from the galaxy's bright core in a roughly northwestern direction, visible in optical photographs as a faint but distinct streak of light. For decades after Curtis's discovery, the jet remained a curiosity without explanation. Astronomers noted its unusual appearance and speculated about its nature, but the theoretical framework needed to understand it did not yet exist. The jet was sometimes interpreted as a stream of stars being ejected from the galaxy, or as a gaseous filament illuminated by some unknown process. The true explanation, involving a supermassive black hole launching relativistic plasma, would not emerge until the latter half of the 20th century. The development of radio astronomy transformed our understanding of M87. The galaxy was identified as a strong radio source, designated Virgo A, one of the brightest radio sources in the sky outside our own galaxy. Radio observations revealed that the emission came not just from the galaxy's core, but also from an extended structure aligned with the optical jet. The jet was not merely a visible light phenomenon, but a source of radiation across the electromagnetic spectrum. As radio telescopes improved in resolution, astronomers began to map the structure of the M87 jet in increasing detail. They found that the jet extended much farther than the optical images suggested, reaching out to distances of several thousand light-years from the galaxy's centre. The jet was not uniform, but showed a series of bright knots along its length, regions of enhanced emission that seemed to mark places of special activity within the flow. The advent of very long baseline interferometry in the 1970s and 80s allowed astronomers to probe the innermost regions of the jet, approaching ever closer to the central black hole. These observations revealed that the jet maintained its structure down to scales of just a few light-years from the nucleus, and that the bright knots appeared to move outward over time. By tracking the motion of these knots over years of observation, astronomers could measure the apparent velocity of material in the jet. The results were startling. Some knots appeared to be moving at speeds exceeding the speed of light, with apparent velocities of 4 to 6 times light speed measured in different observations. This superluminal motion, as we discussed earlier, is an optical illusion created by material moving toward us at nearly the speed of light. Its detection confirmed that the M87 jet contains plasma moving at relativistic velocities, exactly as theoretical models predicted. The Hubble Space Telescope, launched in 1990, provided the clearest optical images of the M87 jet ever obtained. Hubble revealed the jet as a complex structured flow, with bright knots embedded in a more diffuse emission. The knots showed internal structure, with some appearing elongated or showing evidence of shock waves. The overall appearance suggested a highly dynamic environment, with material being accelerated, compressed, and heated as it flowed along the jet. One particularly prominent feature, designated HST-1, lies approximately 1,000 light-years from the galaxy's core and has been the subject of intensive study. In 2005, HST-1 underwent a dramatic brightening, increasing in luminosity by a factor of nearly 100 over a period of several years. This outburst was detected across the electromagnetic spectrum, from radio waves through X-rays, and represented one of the most energetic events ever observed in a jet. The cause of the outburst remains debated, but it may have involved a shockwave propagating through the jet or a magnetic reconnection event that released stored energy. The mass of the black hole powering the M87 jet has been measured through several independent techniques. One method involves observing the motions of stars near the galaxy's center. Stars close to a massive black hole orbit faster than stars farther away, and by measuring these orbital velocities, astronomers can infer the mass of the central object. Observations with the Hubble Space Telescope revealed stars moving at speeds of several hundred kilometers per second within the innermost regions of M87, implying a central mass of several billion solar masses. Another method uses observations of gas disks orbiting the black hole. The Hubble Space Telescope detected a disk of ionized gas at the center of M87, rotating at velocities that could be measured through the Doppler shift of spectral emission lines. The rotation curve of this gas disk provided an independent mass estimate consistent with the stellar dynamical measurement. Both methods converged on a black hole mass of approximately 6 to 7 billion solar masses, making the M87 black hole one of the most massive known. The ultimate confirmation of the black hole's existence came in April 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole shadow. This image, which made headlines around the world, showed a bright ring of emission surrounding a dark central region. The ring represented hot gas orbiting just outside the event horizon, while the dark region was the shadow of the black hole itself, the absence of light caused by photons being captured by the black hole's gravity. The Event Horizon Telescope achieved this remarkable image by linking radio telescopes around the world into a single virtual instrument the size of Earth. This technique, called very long baseline interferometry, allowed the telescope to achieve the angular resolution needed to see structures on the scale of the event horizon, despite the black hole's distance of 55 million light-years. The observation required years of preparation, involving the synchronization of atomic clocks, the collection of petabytes of data, and the development of sophisticated imaging algorithms. The image of the M87 black hole confirmed several theoretical predictions. The size of the shadow is consistent with a black hole of approximately 6.5 billion solar masses, in excellent agreement with previous mass estimates. The asymmetric brightness of the ring, with one side appearing brighter than the other, was consistent with Doppler boosting from material orbiting the black hole at relativistic speeds, and the overall appearance matched predictions from general relativistic simulations of accreting black holes. Perhaps most importantly for our story, the Event Horizon Telescope observations also revealed the base of the jet for the first time. Images showed emission extending away from the black hole shadow in the direction of the known jet, representing the innermost launching region where the jet first forms. These observations provided the first direct glimpse of the connection between the black hole and its jet, confirming that the jet originates from the immediate vicinity of the event horizon. Subsequent observations with the Event Horizon Telescope have continued to refine our understanding of the M87 system. In 2023, the collaboration released images showing the magnetic field structure near the black hole, revealed through the polarization of the radio emission. The magnetic field appeared to be organized in a spiral pattern, consistent with theoretical models of magnetically arrested accretion disks. This organized magnetic field is likely crucial for launching and collimating the powerful jet. The M87 jet has also been observed extensively in X-rays by the Chandra X-ray Observatory. X-ray emission traces the highest energy particles in the jet, electrons that have been accelerated to energies far exceeding what can be achieved in any particle accelerator on Earth. The X-ray observations reveal that particle acceleration continues throughout the length of the jet, not just at the base near the black hole. The mechanism for this distributed acceleration remains a subject of active research. At the largest scales, the M87 jet terminates in enormous radio lobes that extend far beyond the visible galaxy. These lobes span approximately 250,000 light-years from end to end, considerably larger than the Milky Way galaxy. The energy contained in these lobes, accumulated over millions of years of jet activity, is staggering. Estimates suggest that the total energy in the lobes exceeds 10 to the 60 joules, equivalent to the complete conversion of billions of solar masses into pure energy. The influence of the M87 jet extends beyond its immediate surroundings. The jet appears to be heating the gas in the central regions of the Virgo cluster, preventing it from cooling and condensing into new stars. This feedback process, which we will explore in more detail in a later chapter, may be crucial for understanding why massive galaxies like M87 have stopped forming stars despite possessing vast reservoirs of hot gas. The M87 jet has served as a laboratory for testing our understanding of jet physics. Its relative proximity, its favourable orientation, and its impressive power have made it an ideal target for observations across the electromagnetic spectrum. Each new telescope and each new observing technique has revealed new aspects of this remarkable structure, from the event horizon scale base to the cluster scale lobes. The story of the M87 jet is still being written, with each observation adding new chapters to our understanding. While Messier 87 has captured the spotlight in recent years, the universe contains countless other examples of black hole jets, each with its own unique characteristics and scientific lessons. Among the most spectacular and best studied is the jet system in Centaurus A, a peculiar galaxy that offers a different perspective on the jet phenomenon. By examining Centaurus A and other jet sources, we can appreciate the remarkable diversity of these cosmic structures and begin to understand what factors determine their properties. Centaurus A, located approximately 12 million light-years from Earth in the southern constellation Centaurus, is the closest major radio galaxy to our planet. Its proximity makes it an invaluable laboratory for studying jet physics, allowing observations at spatial resolutions impossible for more distant sources. The galaxy itself is unusual, a giant elliptical galaxy crossed by a dramatic lane of dark dust that gives it a distinctive appearance in optical images. The dust lane in Centaurus A is the remnant of a smaller spiral galaxy that collided with and was absorbed by the larger elliptical galaxy sometime in the past few 100 million years. This merger event may have played a role in triggering or enhancing the jet activity we observe today by funneling fresh gas toward the central black hole and disturbing the magnetic field configuration in ways that promoted jet launching. The connection between galaxy mergers and jet activity is an active area of research, with Centaurus A serving as a prime example. The central black hole in Centaurus A is considerably less massive than the monster in M87, containing approximately 55 million solar masses according to recent measurements. This is still an enormous black hole by any standard, more than 10 times the mass of the black hole at the centre of our own Milky Way, but it is nearly 100 times less massive than the M87 black hole. Despite this difference in black hole mass, Centaurus A produces impressive jets that have been studied across the electromagnetic spectrum. The jets of Centaurus A extend in opposite directions from the galaxy's core, as expected from the basic physics of jet formation. The northern jet points roughly toward Earth, while the southern jet points away. This orientation means that the northern jet appears brighter and more prominent due to relativistic beaming effects, the same Doppler boosting that makes one side of the M87 black hole ring appear brighter than the other. Material in the northern jet, moving toward us at relativistic speeds, has its emission amplified, while material in the southern jet, moving away from us, has its emission diminished. At radio wavelengths, the Centaurus A jets extend to enormous distances, creating radio lobes that span approximately 8 degrees on the sky, more than 16 times the apparent diameter of the full moon. Given the galaxy's distance of 12 million light-years, this angular size corresponds to a physical extent of roughly 1.5 million light-years from end to end. The Centaurus, her radio lobes are among the largest structures visible from Earth, though their low surface brightness makes them invisible to the naked eye. The inner regions of the Centaurus A jets have been imaged with exquisite detail using very long baseline interferometry and the Atacama Large Millimeter Array. These observations reveal a jet that is initially broad near the black hole, but becomes progressively more collimated as it propagates outward, exactly as predicted by magnetic collimation models. The collimation appears to occur over distances of a few hundred to a few thousand gravitational radii from the black hole, consistent with observations of other well-resolved jets. One fascinating feature of the Centaurus A jet is the presence of distinct knots and filaments within the flow. Some of these features appear to be stationary, marking locations where the jet interacts with obstacles or where standing shock waves have formed. Others move outward at measurable velocities, tracing the bulk flow of material along the jet. The combination of stationary and moving features creates a complex dynamic structure that changes over timescales of years to decades. X-ray observations of Centaurus A with the Chandra X-ray Observatory have revealed high-energy emission from the jet, indicating the presence of electrons accelerated to extreme energies. The X-ray emission extends along much of the jet's length, suggesting that particle acceleration is occurring throughout the flow, not just at the base near the black hole. The mechanism for this distributed acceleration remains a puzzle, though shockwaves and magnetic reconnection are leading candidates. At the larger scales, the Centaurus A radio lobes show complex structure with filaments, shells, and brightness variations that record the history of jet activity over millions of years. The lobes are not smooth, uniform structures, but rather show evidence of multiple episodes of jet activity, with newer material ploughing into older material and creating layered structures. The overall morphology is classified as Fanaroff-Riley type 1, with the emission concentrated toward the center rather than at the edges, consistent with the relatively modest power of the jets compared to the most luminous radio galaxies. Beyond Centaurus A, the universe contains an astonishing variety of jet-producing systems. Radio galaxies span a range of more than a factor of 1 million in jet power, from relatively feeble sources that barely disturb their surroundings to monsters that outshine entire galaxy clusters. The most powerful radio galaxies, sometimes called quasar-mode sources, produce jets with mechanical powers exceeding 10 to the 39 watts, enough to significantly influence the evolution of their host galaxies and the intergalactic medium around them. At the low-power end of the distribution are sources sometimes called radio-quiet, active galactic nuclei, which show evidence of weak jets or jet-like outflows, but lack the dramatic radio lobes of classical radio galaxies. These sources may represent a different mode of black hole activity, perhaps associated with lower accretion rates or weaker magnetic fields. The boundary between jet-producing and non-jet-producing active galactic nuclei is not sharp, and understanding what determines whether a given black hole will launch jets remains an open question. The morphology of jets varies as widely as their power. Some jets remain remarkably straight over their entire length, maintaining a constant direction from the black hole to the terminal hotspots. Others show dramatic bends and curves, sometimes executing complete reversals of direction. These bent jets are often found in galaxy clusters, where the motion of the host galaxy through the cluster medium creates a ram pressure that deflects the jet from its original path. The resulting structures, sometimes called head-tail or wide-angle tail sources, provide information about both the jet properties and the cluster environment. Some jets show evidence of precession, a slow wobbling of the jet axis over time that creates corkscrew or helical patterns in the large-scale structure. Precession might be caused by the gravitational influence of a second supermassive black hole in a binary system, by warping of the accretion disk, or by other dynamical effects. The precession period can range from thousands to millions of years, and the resulting structures can extend over enormous volumes of space. The composition of jets also appears to vary from source to source. Some jets show clear evidence of containing normal matter, with spectral features indicating the presence of atoms and ions. Others appear to be dominated by electron-positron pairs, the antimatter counterparts of ordinary electrons. Still others may contain a mixture of both components. The composition affects how the jet interacts with its environment and how efficiently it can transfer energy to its surroundings. The host galaxies of jet-producing black holes span a range of types, though certain patterns emerge. The most powerful jets tend to be found in massive elliptical galaxies, which typically host the most massive black holes. These galaxies have usually experienced multiple merger events in their history, which may have contributed to the growth of their central black holes and the accumulation of the magnetic flux needed for jet launching. Spiral galaxies like our own Milky Way rarely produce powerful jets, though some do show evidence of weak jet activity. The environment surrounding the host galaxy also influences jet properties. Jets propagating through dense cluster environments encounter more resistance and may be disrupted or deflected more easily than jets in lower density surroundings. The interaction between jet and environment can create spectacular structures, including cavities and bubbles in the hot cluster gas, shock waves that propagate through the intergalactic medium, and filaments of cooling gas that condense in the wake of the jet. The diversity of black hole jets reflects the diversity of conditions in which they form and propagate. No two jets are exactly alike, and each offers unique insights into the physics of relativistic outflows. By studying jets across the full range of powers, morphologies, and environments, astronomers can test theoretical models and identify the key parameters that control jet behavior. This comparative approach has been essential for developing our current understanding and will continue to guide future research. The plasma within black hole jets moves at velocities that approach the ultimate speed limit of the universe, the speed of light. At these extreme velocities, the familiar laws of Newtonian physics no longer apply, and we must turn to Einstein's special theory of relativity to understand what is happening. The relativistic nature of jets produces a range of fascinating effects, from the apparent superluminal motion we have already mentioned to dramatic changes in how we perceive time, distance, and energy. Special relativity, published by Einstein in 1905, rests on two fundamental postulates. First, the laws of physics are the same for all observers moving at constant velocities relative to one another. There is no preferred reference frame, no absolute state of rest against which all motion can be measured. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. This second postulate seems innocuous at first glance, but its implications are profound and far-reaching. If the speed of light is truly constant for all observers, then something else must give way to accommodate this constancy. That something turns out to be our intuitive notions of space and time. In special relativity, space and time are not separate, absolute entities, but are woven together into a four-dimensional fabric called space-time. Different observers moving at different velocities will disagree about the lengths of objects and the durations of events. These disagreements are not errors or illusions, but reflect the genuine relativity of space and time. One of the most famous consequences of special relativity is time dilation. A clock moving relative to an observer will appear to tick more slowly than an identical clock at rest. The faster the moving clock travels, the more pronounced this slowing becomes. At everyday speeds, the effect is negligible, far too small to notice. But as velocities approach the speed of light, time dilation becomes dramatic. A clock moving at 90% of light speed would tick at less than half the rate of a stationary clock. At 99% of light speed, the moving clock would tick at only about 1/7 the stationary rate. For particles in black hole jets, moving at 99% or more of light speed, time dilation has significant physical consequences. Unstable particles that would normally decay in microseconds can survive for much longer periods, as measured by outside observers, because time passes more slowly in the particle's reference frame. This extended lifetime allows particles to travel much farther than they otherwise could, contributing to the enormous lengths of astrophysical jets. Closely related to time dilation is length contraction. An object moving relative to an observer will appear shortened along the direction of motion. Like time dilation, this effect is negligible at everyday speeds but becomes pronounced at relativistic velocities. A meter stick moving at 90% of light speed would appear only about 44 centimeters long to a stationary observer. At 99% of light speed, it would appear less than 15 centimeters long. Length contraction affects how we interpret observations of jets. The actual physical length of a jet, as measured in the jet's own reference frame, may differ substantially from the length we observe from Earth. The relativistic motion compresses the apparent structure along the direction of motion, potentially affecting our measurements of jet opening angles and internal structures. Perhaps the most counterintuitive consequence of special relativity is the relativity of simultaneity. Events that appear simultaneous to one observer may occur at different times according to another observer moving at a different velocity. This is not a matter of perception or signal delay, but a fundamental property of space-time itself. Two events that are genuinely simultaneous in one reference frame are genuinely non-simultaneous in another frame, and neither frame is more correct than the other. The energy of a moving object also behaves differently in special relativity than in Newtonian physics. The famous equation E equals mc squared tells us that mass and energy are equivalent, with a small amount of mass corresponding to an enormous amount of energy. For a moving object, the total energy includes both this rest mass energy and the kinetic energy of motion. As an object approaches the speed of light, its kinetic energy grows without bound, which is why accelerating a massive object to exactly light speed would require infinite energy. The particles in black hole jets carry enormous kinetic energies due to their relativistic velocities. A single proton moving at 99.9% of light speed carries kinetic energy equivalent to about 20 times its rest mass energy. When such particles collide with stationary matter or with each other, they can produce showers of secondary particles and intense radiation. This is one mechanism by which jets transfer their energy to their surroundings. Now let us turn to one of the most striking relativistic effects observed in black hole jets, superluminal motion. As we mentioned earlier, bright knots in some jets appear to move across the sky at speeds exceeding the speed of light, sometimes by factors of several. This observation initially caused great consternation among astronomers, as it seemed to violate the fundamental speed limit of special relativity. However, superluminal motion is not actual faster than light travel, but rather an optical illusion created by the geometry of relativistic motion toward the observer. To understand superluminal motion, imagine a bright blob of plasma moving along a jet that is oriented at a small angle to our line of sight. The blob is moving toward us, though not directly toward us, at a velocity close to the speed of light. As the blob moves, it emits light that travels to Earth. Because the blob is moving toward us, each successive light signal has a shorter distance to travel than the previous one. The light signals bunch up, arriving at Earth with smaller time intervals between them than the actual time intervals at which they were emitted. This bunching of light signals makes the blob appear to cross the sky faster than it actually is moving. If the geometry is right, with the jet oriented at a sufficiently small angle to our line of sight and the blob moving at a sufficiently high velocity, the apparent transverse velocity can exceed the speed of light. The effect is maximized when the jet makes an angle to the line of sight whose sine equals the ratio of the blob's velocity to the speed of light. Superluminal motion has been observed in numerous black hole jets, including the famous jet in Messier 87. Measurements of knot motions in the M87 jet have revealed apparent velocities of 4 to 6 times the speed of light, implying actual velocities of more than 99% of light speed. These observations confirm that jets contain material moving at extreme relativistic velocities, exactly as theoretical models predict. Another important relativistic effect in jets is Doppler boosting, also called relativistic beaming. When a source of radiation is moving toward an observer at relativistic speeds, the observed intensity of the radiation is dramatically enhanced compared to what would be observed if the source were stationary. Conversely, when the source is moving away from the observer, the intensity is diminished. This effect arises from a combination of time dilation, length contraction, and the Doppler shift of the radiation frequency. The magnitude of Doppler boosting depends on the velocity of the source and the angle between the velocity and the line of sight. For a source moving directly toward the observer at 99% of light speed, the boosting factor can exceed 100, meaning the source appears more than 100 times brighter than it would if stationary. For a source moving directly away at the same speed, the dimming factor is equally dramatic, making the source appear more than 100 times fainter. Doppler boosting explains why we often see only one jet from systems that should produce two oppositely directed jets. The jet pointing toward us is boosted to high brightness, while the jet pointing away is dimmed to near invisibility. In Messier 87, for example, the main jet is clearly visible, but the counterjet on the opposite side of the black hole is extremely faint and was only detected after careful observations designed to find it. The brightness ratio between jet and counterjet provides information about the jet velocity and orientation. The Doppler effect also shifts the frequency of radiation from moving sources. Light from a source moving toward us is shifted to higher frequencies, toward the blue end of the spectrum. Light from a source moving away is shifted to lower frequencies, toward the red end. For relativistic velocities, this Doppler shift can be substantial, moving radiation from one part of the electromagnetic spectrum to another. In black hole jets, Doppler shifting affects how we interpret observations at different wavelengths. Radiation that was emitted as radio waves in the jet's reference frame might be observed as millimeter waves, or even infrared light in our reference frame, depending on the jet velocity and orientation. Astronomers must account for these shifts when comparing observations at different wavelengths and when inferring the intrinsic properties of the emitting plasma. The combination of time dilation, length contraction, Doppler boosting, and frequency shifting creates a complex observational picture that requires careful analysis to interpret. What we see when we observe a relativistic jet is not a simple snapshot of the jet's current state, but a distorted view shaped by the relativistic motion of the emitting material. Disentangling the intrinsic jet properties from these relativistic effects is one of the challenges of jet astrophysics. Beyond special relativity, the regions closest to black holes require the full machinery of general relativity to describe. General relativity, Einstein's theory of gravity published in 1915, describes how mass and energy curve the fabric of space-time, and how this curvature affects the motion of objects and the propagation of light. Near a black hole, where space-time curvature is extreme, general relativistic effects become dominant. One important general relativistic effect is gravitational redshift. Light climbing out of a gravitational well loses energy and shifts to longer wavelengths. Near a black hole, this redshift can be substantial. Light emitted from just outside the event horizon is redshifted to nearly infinite wavelength, which is another way of understanding why nothing can escape from inside the horizon. For jets, gravitational redshift affects radiation emitted from the innermost launching regions, though by the time the jet has propagated to observable distances, this effect is usually small compared to the Doppler effects from bulk motion. Another general relativistic effect is the dragging of spacetime by a rotating black hole, which we discussed in the context of the Blandford-Znajek mechanism. This frame dragging, as it is called, causes objects near the black hole to be pulled along in the direction of the black hole's rotation, even if they are trying to remain stationary. The frame dragging effect is crucial for understanding how energy is extracted from spinning black holes to power jets. General relativity also predicts the existence of the innermost stable circular orbit, the closest distance at which matter can orbit a black hole without spiraling inward. For a non-rotating black hole, this orbit lies at 3 times the Schwarzschild radius. For a maximally rotating black hole, it can be as close as the event horizon itself. The location of the innermost stable circular orbit affects the structure of the accretion disk and the launching region of the jet. The interplay between special and general relativistic effects makes the physics of black hole jets extraordinarily rich and complex. Numerical simulations that attempt to model jet formation and propagation must incorporate both theories, solving Einstein's equations for the curved spacetime near the black hole, while also tracking the relativistic motion of plasma through that spacetime. These simulations have become increasingly sophisticated over the past few decades, providing insights that complement and guide observational studies. One remarkable prediction of relativistic jet physics is that jets should be able to accelerate particles to energies far exceeding what can be achieved in any terrestrial particle accelerator. The Large Hadron Collider, the most powerful accelerator on Earth, can accelerate protons to energies of about 7 trillion electron volts. Black hole jets, by contrast, appear capable of accelerating particles to energies of 10 to the 20 electron volts, or more, roughly 10 million times higher. These ultra-high energy cosmic rays, detected by observatories on Earth, may originate in the relativistic shocks and turbulence of black hole jets. The mechanism by which jets accelerate particles to such extreme energies remains an active area of research. Shock acceleration, where particles bounce back and forth across a shock front and gain energy with each crossing, is one leading candidate. Magnetic reconnection, where tangled magnetic field lines suddenly rearrange and release stored energy, is another. Turbulent acceleration, where particles scatter off magnetic irregularities in a turbulent flow, may also contribute. All of these processes are enhanced by the relativistic nature of the jet, which provides the extreme conditions needed for efficient particle acceleration. As we contemplate the relativistic physics of black hole jets, we are reminded of how far our understanding of nature has come since Einstein's revolutionary insights more than a century ago. The same principles that explain the constancy of the speed of light and the equivalence of mass and energy also explain the superluminal illusions and Doppler boosting we observe in distant jets. The universe operates according to consistent physical laws that we have been privileged to discover and that continue to reveal new wonders as we apply them to ever more extreme environments. Black hole jets are not merely spectacular light shows in the distant cosmos. They are active agents of change, powerful enough to reshape the galaxies that host them and to influence the evolution of matter across millions of light years. The influence of jets begins in the immediate vicinity of the host galaxy. As a jet propagates outward from the central black hole, it must first traverse the interstellar medium of the galaxy itself. This medium consists of gas and dust distributed throughout the galaxy, the raw material from which new stars form. The jet plows through this material at relativistic speeds, creating shock waves that heat and compress the gas. The interaction between jet and interstellar medium can have dramatic consequences for star formation. In some cases, the shock waves triggered by the jet may actually enhance star formation by compressing gas clouds to the point where they become gravitationally unstable and collapse. Observations of some jet-hosting galaxies have revealed regions of active star formation aligned with the jet axis, suggesting that the jet has triggered the birth of new stars. More commonly, however, jets appear to suppress star formation rather than enhance it. The energy deposited by the jet heats the surrounding gas, increasing its pressure and making it more difficult for the gas to collapse under its own gravity. Hot gas is less likely to form stars than cold gas, so by heating the interstellar medium, jets can effectively shut down star formation in their host galaxies. This suppression of star formation is one aspect of what astronomers call active galactic nucleus feedback. The concept of feedback is central to modern theories of galaxy evolution. Without some mechanism to regulate star formation, theoretical models predict that massive galaxies should contain far more stars than we actually observe. The gas in and around these galaxies should cool and condense, forming stars at prodigious rates until the gas supply is exhausted. Yet observations show that the most massive galaxies have largely stopped forming stars, despite possessing vast reservoirs of hot gas that could potentially cool and fuel star formation. Black hole jets provide a natural solution to this puzzle. By injecting energy into the surrounding gas, jets can prevent the gas from cooling and condensing, maintaining it in a hot, diffuse state that is unable to form stars. The energy output of a powerful jet is more than sufficient to offset the radiative cooling of gas in even the most massive galaxies and galaxy clusters. Jets thus act as thermostats, regulating the temperature of the surrounding gas and controlling the rate at which new stars can form. The evidence for jet feedback comes from multiple sources. X-ray observations of galaxy clusters have revealed cavities or bubbles in the hot intracluster gas, regions of reduced X-ray emission that coincide with the radio lobes of central jet sources. These cavities are filled with relativistic plasma from the jets, which has displaced the thermal gas and created voids in the X-ray emission. The energy required to inflate these cavities can be estimated from their size and the pressure of the surrounding gas, and it typically matches the energy output expected from the central black hole. The cavities observed in galaxy clusters can be enormous, spanning hundreds of thousands of light years, and containing energy equivalent to millions of supernova explosions. The most powerful examples rival the total gravitational binding energy of small galaxies. Yet this energy is deposited gently over millions of years rather than in a single explosive event. The jets inflate the cavities gradually, pushing aside the surrounding gas without creating the violent shocks that would be produced by a sudden energy release. This gentle energy deposition is crucial for effective feedback. If the jet energy were released too quickly, it would create strong shocks that would heat the gas to extreme temperatures, but would also allow the gas to cool rapidly through radiation. The gentle, continuous energy input from jets maintains the gas at a moderate temperature, hot enough to prevent star formation, but not so hot that it radiates away its energy quickly. This balance allows jets to regulate star formation over cosmological timescales. Beyond the immediate host galaxy, jets can influence the intergalactic medium, the sparse gas that fills the space between galaxies. In galaxy clusters, this intergalactic gas is heated to temperatures of tens of millions of degrees by the gravitational energy released as the cluster formed. The hot gas emits X-rays and would gradually cool over time if not for the energy input from central jet sources. Observations suggest that jet heating is essential for maintaining the thermal balance of galaxy clusters. Clusters with strong central radio sources show evidence of recent jet activity, with cavities and shock waves visible in X-ray images. Clusters without strong radio sources often show evidence of cooling flows, where the central gas is cooling and condensing toward the cluster center. The presence or absence of jet activity appears to determine whether a cluster maintains its hot atmosphere or develops a cooling core. The feedback loop between black hole jets and their surroundings is self-regulating to some degree. When the surrounding gas is hot and diffuse, little material falls toward the central black hole, and jet activity is weak. As the gas cools and condenses, more material becomes available to fuel the black hole, and jet activity increases. The increased jet activity heats the gas, reducing the fuel supply and eventually causing the jets to weaken. This cycle of heating and cooling, activity and quiescence may repeat many times over the lifetime of a galaxy or cluster. Evidence for this cyclical behavior comes from observations of multiple generations of cavities in some galaxy clusters. The innermost cavities closest to the central galaxy represent the most recent episode of jet activity. Farther out, older cavities mark the locations of previous active episodes, now displaced from the center by the buoyant rise of the relativistic plasma through the surrounding gas. By counting and dating these cavities, astronomers can reconstruct the history of jet activity over tens to hundreds of millions of years. The influence of jets extends beyond thermal effects to include the transport of magnetic fields and relativistic particles into the intergalactic medium. The plasma that fills jet lobes contains magnetic fields that were generated near the black hole and carried outward by the jet flow. When the lobes eventually dissipate, these magnetic fields are released into the surrounding medium, contributing to the magnetization of intergalactic space. The origin of magnetic fields in the intergalactic medium is a long-standing puzzle in astrophysics. Observations indicate that magnetic fields are present throughout the universe, even in regions far from any obvious source. Jets from active galactic nuclei may be one of the primary mechanisms for seeding these fields, distributing magnetized plasma across vast volumes of space over cosmic time. The cumulative effect of billions of jet sources over the history of the universe could account for much of the observed intergalactic magnetization. Similarly, the relativistic particles accelerated in jets and their lobes can escape into the intergalactic medium, contributing to the population of cosmic rays that permeates the universe. These cosmic rays, consisting primarily of protons and heavier atomic nuclei, accelerated to extreme energies, are detected on Earth when they collide with atoms in the upper atmosphere. The highest energy cosmic rays may originate in the powerful shocks associated with black hole jets, making jets one of the most extreme particle accelerators in nature. The chemical enrichment of the intergalactic medium may also be influenced by jets. As jets propagate through their host galaxies, they can entrain material from the interstellar medium, carrying it outward into intergalactic space. This material includes heavy elements produced by stellar nucleosynthesis, elements like carbon, oxygen, and iron that are essential for the formation of planets and life. By transporting these elements beyond the boundaries of galaxies, jets contribute to the chemical evolution of the universe as a whole. On the largest scales, jets may influence the formation and evolution of cosmic structure itself. The energy injected by jets into the intergalactic medium affects the pressure and temperature of the gas, which in turn affects how gas flows into and out of galaxies. Simulations of cosmic structure formation that include jet feedback produce results that more closely match observations than simulations without feedback, suggesting that jets play an important role in shaping the universe we observe. The recognition of jets as cosmic sculptors represents a major shift in our understanding of galaxy evolution. For much of the 20th century, galaxies were viewed as relatively isolated systems, evolving primarily through internal processes like star formation and stellar death. The discovery that central black holes can profoundly influence their host galaxies and surroundings has revealed a more interconnected picture, where the smallest scales of black hole physics are linked to the largest scales of cosmic structure. This interconnection raises profound questions about the coevolution of black holes and galaxies. Observations have revealed tight correlations between the masses of central black holes and the properties of their host galaxies, such as the total stellar mass and the velocity dispersion of stars. These correlations suggest that black holes and galaxies grow together, each influencing the other's evolution. Jet feedback may be one of the key mechanisms establishing and maintaining these correlations. As we contemplate the role of jets in shaping the cosmos, we gain a new appreciation for the power of these structures. What appears in our telescopes as a faint streak of light is actually a conduit for enormous amounts of energy, capable of influencing the evolution of matter across millions of light years. The jets are not passive features of the universe, but active participants in its ongoing transformation, sculptors working on a canvas of cosmic proportions. Like living organisms, black hole jets are born, evolve, and eventually fade away. The life cycle of a jet spans millions of years, from the initial ignition near the black hole to the final dissipation of the radio lobes into the intergalactic medium. Understanding this life cycle is essential for interpreting the diverse population of jet sources we observe, and for understanding the cumulative impact of jets on the universe over cosmic time. The birth of a jet requires a specific set of conditions near the central black hole. A supermassive black hole must be present, preferably one that is rotating rapidly. An accretion disk must surround the black hole, providing both the fuel for the system and the anchor points for magnetic field lines. And strong, organized magnetic fields must thread through the disk and the black hole's ergosphere, providing the mechanism for extracting and channeling energy into the jet. These conditions are not always satisfied. Many supermassive black holes exist in a quiescent state, with little or no accretion and no significant jet activity. The black hole at the centre of our own Milky Way, Sagittarius A star, is an example. Despite its mass of 4 million solar masses, Sagittarius A star currently produces only feeble jets, if any, because it lacks a substantial accretion disk. The gas supply in its vicinity is too sparse to fuel significant activity. Jet ignition occurs when sufficient gas becomes available to the black hole, and when the magnetic field configuration becomes favourable for jet launching. The trigger for ignition might be a galaxy merger that funnels gas toward the centre, a tidal disruption event where a star wanders too close to the black hole and is torn apart, or simply the gradual accumulation of gas from stellar winds and other sources. Whatever the trigger, the result is the establishment of an accretion flow and the launching of relativistic jets along the rotation axis. The early stages of jet evolution are characterized by rapid growth and expansion. The newly launched jet must first punch through the interstellar medium of the host galaxy, displacing gas and creating a channel through which subsequent jet material can flow. This initial breakthrough phase may be accompanied by strong shocks and intense radiation as the jet interacts with the dense gas near the galactic center. As the jet clears a path through the galaxy, it begins to propagate into the less dense intergalactic medium. The jet's advance slows as it encounters resistance from the external gas, but it continues to push outward, inflating lobes of relativistic plasma on either side of the host galaxy. The lobes grow in size as more material flows through the jet, accumulating the spent plasma that has passed through the terminal shock. During this active phase, the jet maintains a continuous connection between the black hole and the outer lobes. Energy and momentum flow steadily outward, replenishing the lobes and driving their continued expansion. The jet itself may show variability on various timescales, with bright knots forming and propagating outward, but the overall structure remains intact. This active phase can last for tens of millions of years, depending on the fuel supply available to the black hole. The structure of the jet during the active phase reflects the balance between the jet's internal pressure and the external pressure of the surrounding medium. In regions where the external pressure is high, the jet is confined to a narrow channel. In regions where the external pressure is low, the jet can expand more freely. The transition between these regimes often occurs at the boundary of the host galaxy, where the dense interstellar medium gives way to the more tenuous intergalactic medium. The morphology of the lobes during the active phase depends on the jet power and the properties of the external medium. Powerful jets in low-density environments produce the classic Fanneroff-Riley type 2 morphology, with bright hotspots at the outer edges of the lobes, marking the current working surface of the jet. Less powerful jets, or jets in denser environments, produce the Fanneroff-Riley type 1 morphology, with more diffuse lobes and no clear hotspots. Eventually, the fuel supply to the black hole diminishes and the jet begins to weaken. This decline might occur gradually as the accretion rate slowly decreases, or it might occur abruptly if the fuel supply is suddenly cut off. As the jet weakens, it can no longer maintain its structure against the pressure of the surrounding medium. The jet becomes disrupted, breaking up into disconnected blobs and filaments that no longer form a coherent flow. When the jet finally turns off, the lobes are cut off from their energy supply. They no longer receive fresh relativistic plasma from the central engine, and they begin to fade. The energetic particles within the lobes lose their energy through radiation and through interactions with low-energy photons. The magnetic field weakens as the lobes expand and as magnetic reconnection converts organized field energy into heat. Over millions of years, the once bright lobes dim to ghostly remnants, visible only at the lowest radio frequencies, where the oldest, lowest energy particles still emit. These remnant lobes, sometimes called radio relics or radio ghosts, provide a fossil record of past jet activity. By studying their properties, astronomers can learn about the history of jet activity in individual galaxies and in the universe as a whole. The prevalence of remnant lobes suggests that jet activity is episodic with active phases separated by quiescent intervals during which the lobes fade. The duration of the quiescent phase between active episodes is not well constrained by observations. It might be comparable to the active phase, lasting tens of millions of years, or it might be much longer. The trigger for reactivation is also uncertain. A new supply of gas, perhaps from a minor merger or from cooling of the hot halo gas, might reignite the jet. Alternatively, the black hole might remain quiescent for billions of years, never again producing significant jets. Some galaxies show evidence of multiple episodes of jet activity, with nested sets of lobes at different distances from the center. The innermost lobes represent the most recent active episode, while the outer lobes are remnants of earlier episodes. These double-double radio galaxies, as they are sometimes called, provide direct evidence for the episodic nature of jet activity and allow astronomers to estimate the duration of active and quiescent phases. The life cycle of jets has important implications for their cumulative impact on the universe. If jets are active for only a small fraction of the time, their instantaneous power must be correspondingly higher to achieve the same time-averaged energy output. Conversely, if jets are active for most of the time, their instantaneous power can be lower. The duty cycle of jet activity, the fraction of time that a typical black hole spends in an active jet-producing state, is a key parameter for understanding the role of jets in galaxy evolution and cosmic feedback. Estimates of the jet duty cycle vary depending on the method used and the type of galaxy considered. For the most massive elliptical galaxies in cluster centers, the duty cycle appears to be high, perhaps 50% or more. These galaxies show frequent evidence of recent jet activity, with cavities and shock waves visible in X-ray observations. For less massive galaxies, the duty cycle may be lower, with longer quiescent intervals between active episodes. The evolution of jet activity over cosmic time is another important aspect of the jet life cycle. Observations indicate that powerful jets were more common in the early universe, when galaxies were younger and gas supplies were more abundant. The peak of quasar activity occurred roughly 10 billion years ago, when the universe was only a few billion years old. Since then, the overall level of jet activity has declined as gas supplies have been consumed and as galaxies have settled into more quiescent states. This cosmic evolution of jet activity has implications for the cumulative impact of jets on the universe. Much of the energy injected by jets into the intergalactic medium was deposited early in cosmic history, when jets were more common and more powerful. The magnetic fields and relativistic particles distributed by ancient jets may still permeate intergalactic space today, even though the jets themselves faded long ago. As we trace the life cycle of black hole jets, we see a story of birth, growth, decline, and renewal. Each jet is a temporary structure, lasting for a cosmic eye blink before fading into the background. Yet the cumulative effect of countless jets over billions of years has shaped the universe we observe, regulating star formation in galaxies, heating gas in clusters, and seeding intergalactic space with magnetic fields and energetic particles. The life cycle of individual jets is part of a larger cosmic cycle, connecting the physics of black holes to the evolution of the universe as a whole. The study of black hole jets has been transformed in recent years by a new generation of telescopes and observational techniques. From the Event Horizon scale images of the Event Horizon telescope to the wide-field surveys of next-generation radio arrays, astronomers now have unprecedented tools for probing the physics of jets across all scales. The Event Horizon telescope, which we encountered in our discussion of Messier 87, represents the pinnacle of angular resolution in astronomy. By linking radio telescopes around the world into a single virtual instrument, the Event Horizon Telescope achieves an angular resolution equivalent to reading a newspaper in New York from a cafe in Paris. This extraordinary resolution allows astronomers to image structures on the scale of the event horizon itself, revealing the innermost regions where jets are launched. The first Event Horizon Telescope image of the M87 black hole, released in April 2019, showed the shadow of the black hole surrounded by a bright ring of emission. Subsequent observations have revealed additional details, including the structure of the magnetic field near the black hole and the connection between the black hole and the base of the jet. These observations have confirmed key predictions of theoretical models and have opened new avenues for testing our understanding of jet physics. The Event Horizon Telescope has also observed Sagittarius A star, the supermassive black hole at the centre of our own Milky Way. Images released in 2022 showed a similar ring structure, though the smaller mass of Sagittarius A star means that the emission varies on much shorter timescales, making imaging more challenging. Sagittarius A star does not currently produce a powerful jet, but the Event Horizon Telescope observations provide a baseline for understanding the conditions near a relatively quiescent supermassive black hole. Future upgrades to the Event Horizon Telescope will add new stations and extend observations to higher frequencies, improving both the resolution and the image quality. The next generation Event Horizon Telescope, currently in the planning stages, aims to produce movies of the material orbiting black holes, capturing the dynamics of accretion and jet launching in real time. These movies would provide unprecedented insights into the processes that power jets. At longer radio wavelengths, new facilities are revolutionizing our view of jets on larger scales. The Carl G. Jansky Very Large Array in New Mexico, upgraded in 2012, provides improved sensitivity and frequency coverage for studying jet structure and polarization. The Australian Square Kilometre Array Pathfinder and the South African Meerkat Telescope are precursors to the Square Kilometre Array, an international project that will be the largest radio telescope ever built when completed. The Square Kilometre Array, with collecting area approaching 1 square kilometre, distributed across thousands of individual antennas, will detect radio emission from jets at unprecedented distances and with unprecedented sensitivity. It will survey the entire sky for radio sources, discovering millions of new jets and providing a complete census of jet activity across cosmic time. The statistical power of this survey will allow astronomers to address questions about jet demographics, duty cycles, and evolution that cannot be answered with current samples. At X-ray wavelengths, the Chandra X-ray Observatory has been the workhorse for jet studies since its launch in 1999. Chandra's sharp X-ray vision has revealed the high-energy emission from jets, tracing the most energetic particles and the regions of strongest magnetic fields. Chandra observations have shown that particle acceleration occurs throughout the length of jets, not just at the base, and have revealed the cavities and shock waves that jets create in the hot gas of galaxy clusters. Future X-ray missions will build on Chandra's legacy. The Athena mission, planned by the European Space Agency for launch in the late 2030s, will provide greatly improved sensitivity for studying the hot gas in galaxies and clusters, allowing more detailed measurements of jet feedback. The proposed Lynx mission, if approved, would provide Chandra-like angular resolution with much greater collecting area, enabling studies of jets in distant galaxies that are currently beyond reach. At gamma-ray energies, the Fermi Gamma-ray Space Telescope has detected emission from hundreds of jets, primarily from blazars, where the jet is pointed almost directly at Earth. These gamma-ray observations probe the highest energy particles in jets and provide constraints on the mechanisms of particle acceleration. Ground-based gamma-ray observatories, such as the Cherenkov Telescope Array, currently under construction, will extend these observations to even higher energies, potentially detecting emission from the most extreme acceleration events in jets. Optical and infrared observations continue to play an important role in jet studies. The Hubble Space Telescope has provided iconic images of jets in visible light, revealing their structure and variability. The James Webb Space Telescope, launched in 2021, observes at infrared wavelengths that can penetrate the dust obscuring many active galactic nuclei, providing new views of jet launching regions. Ground-based optical telescopes with adaptive optics can now achieve angular resolutions approaching those of space telescopes, allowing detailed studies of jet structure from the ground. The combination of observations across the electromagnetic spectrum, from radio waves through gamma rays, provides a comprehensive picture of jet physics that no single wavelength can offer alone. Radio observations trace the synchrotron emission from relativistic electrons spiraling around magnetic field lines, revealing the overall structure of jets and lobes. Infrared observations can penetrate dusty regions and detect thermal emission from heated material. Optical observations show the highest frequency synchrotron emission and can detect emission lines from ionized gas. X-ray observations trace the most energetic particles and reveal the hot gas that jets interact with. And gamma-ray observations probe the extreme acceleration processes that occur in jets. This multi-wavelength approach has been essential for understanding the physics of jets. By comparing observations at different wavelengths, astronomers can determine the energy distribution of particles in jets, the strength and structure of magnetic fields, and the mechanisms by which jets interact with their surroundings. The coordination of observations across different telescopes and wavelengths has become a standard practice in jet research, with major campaigns organised to observe individual sources simultaneously across the spectrum. Polarization observations provide another powerful tool for studying jets. Synchrotron radiation, the primary emission mechanism in jets, is intrinsically polarized, with the electric field vector aligned perpendicular to the magnetic field direction. By measuring the polarization of jet emission, astronomers can map the magnetic field structure within jets, revealing the twisted, helical configurations predicted by theoretical models. The Event Horizon telescope's polarization observations of Messier 87, released in 2021, showed a spiral pattern of polarization near the black hole, indicating an organized magnetic field threading through the emission region. This observation provided strong support for models in which magnetic fields play a central role in jet launching and collimation. Similar polarization studies at other wavelengths have revealed the magnetic field structure throughout the length of jets, from the launching region to the terminal lobes. Time domain observations, which track how jets change over time, have revealed the dynamic nature of these structures. Jets are not static features, but constantly evolving systems, with bright knots appearing, moving, and fading over timescales of months to years. By monitoring jets over extended periods, astronomers can track the motion of features within the jet, measure velocities, and study the variability of the central engine. The advent of wide-field survey telescopes has enabled systematic studies of jet populations. Surveys like the Very Large Array, Sky Survey, and the Rapid ASCAP Continuum Survey are mapping the radio sky with unprecedented sensitivity and coverage, discovering thousands of new jet sources and providing statistical samples for population studies. These surveys reveal the demographics of jets, showing how jet properties vary with black hole mass, host galaxy type, and cosmic epoch. Citizen science projects have also contributed to jet research. Projects like Radio Galaxies Zoo enlist volunteers to classify radio sources in survey images, identifying jets and lobes and matching them to their host galaxies. The collective effort of thousands of volunteers can process far more data than professional astronomers alone, accelerating the pace of discovery and uncovering rare or unusual sources that might otherwise be overlooked. Computational advances have kept pace with observational progress. Modern supercomputers can simulate jet formation and propagation with unprecedented realism, incorporating general relativistic effects near the black hole, magneto-hydrodynamic processes in the jet, and interactions with the surrounding medium. These simulations produce synthetic observations that can be compared directly with real data, testing theoretical models and guiding the interpretation of observations. Machine learning techniques are increasingly being applied to jet research. Neural networks can be trained to identify jets in survey images, classify their morphologies, and measure their properties automatically. These techniques can process the vast data volumes produced by modern surveys far more quickly than human inspection, enabling studies of jet populations at scales previously impossible. The combination of new observational facilities, advanced computational techniques, and innovative analysis methods has ushered in a golden age for jet research. Questions that seemed unanswerable a generation ago are now being addressed with real data. The connection between black holes and jets, the mechanisms of particle acceleration, the role of jets in galaxy evolution, all of these topics are being illuminated by the flood of new observations and simulations. Looking ahead, the next decade promises even more dramatic advances. The square-kilometre array, when completed, will survey the radio sky with sensitivity and resolution far exceeding current capabilities. The next generation Event Horizon Telescope will produce movies of black hole accretion and jet launching. New X-ray and gamma-ray missions will probe the highest energy processes in jets, and continued advances in computing will enable simulations of ever greater realism and scope. The story of jet observations is a story of technological progress, enabling scientific discovery. Each new telescope and each new technique has revealed aspects of jets that were previously hidden, expanding our understanding and raising new questions. The jets themselves have not changed, but our ability to see and comprehend them has grown enormously. As we continue to develop new tools for observing the universe, we can expect the story of black hole jets to continue unfolding, revealing new wonders and deepening our appreciation for these remarkable cosmic structures. Despite the tremendous progress in understanding black hole jets, many fundamental questions remain unanswered. These open questions define the frontier of jet research, guiding observations and theoretical work toward new discoveries. One of the most basic questions about jets concerns their composition. What are jets actually made of? This seemingly simple question has proven surprisingly difficult to answer. Jets could be composed primarily of electrons and positrons, the antimatter counterparts of electrons. They could be composed of electrons and protons, ordinary matter similar to what makes up our bodies and our planet. Or they could contain a mixture of both, with different components dominating in different regions or at different times. The composition of jets matters because it affects how jets interact with their surroundings and how efficiently they can transfer energy. A jet composed of electron-positron pairs would be much lighter than a jet composed of electrons and protons for the same total energy. The lighter jet would be easier to accelerate to relativistic speeds, but would carry less momentum and would interact differently with external material. Determining the composition is essential for understanding jet energetics and feedback. Observational constraints on jet composition have been difficult to obtain. The radiation we observe from jets comes primarily from electrons, regardless of whether protons are present, because electrons radiate much more efficiently than protons at the same energy. Protons in jets would be largely invisible to our telescopes, making their presence hard to confirm or rule out. Some indirect evidence suggests that at least some jets contain significant proton content, but the question remains open. Another major unsolved problem concerns the mechanism of particle acceleration in jets. We know that jets contain particles accelerated to extreme energies, far exceeding what can be achieved in terrestrial accelerators. But how exactly does this acceleration occur? Several mechanisms have been proposed, including shock acceleration, magnetic reconnection, and turbulent acceleration. But the relative importance of these mechanisms and the details of how they operate remain uncertain. Shock acceleration, also known as diffusive shock acceleration or Fermi acceleration, occurs when particles bounce back and forth across a shock front, gaining energy with each crossing. This mechanism is well established in other astrophysical contexts, such as supernova remnants, and likely operates in jets as well. However, shock acceleration alone may not be able to explain the highest energy particles observed, and other mechanisms may be needed. Magnetic reconnection occurs when tangled magnetic field lines suddenly rearrange, releasing stored magnetic energy and accelerating particles. Reconnection events can be very efficient at accelerating particles to high energies, and they may be particularly important in the magnetically dominated regions near the jet base. However, the conditions under which reconnection occurs and its overall contribution to jet energetics are still being investigated. Turbulent acceleration occurs when particles scatter off magnetic irregularities in a turbulent flow, gradually gaining energy through many small interactions. This mechanism could operate throughout the volume of a jet, providing distributed acceleration that might explain the extended high-energy emission observed in some sources. However, the efficiency of turbulent acceleration and its dependence on jet properties are not well constrained. Understanding particle acceleration in jets has implications beyond jet physics. Jets may be the sources of ultra-high energy cosmic rays, the most energetic particles ever detected. These cosmic rays have energies exceeding 10 to the 20 electron volts, millions of times higher than the energies achieved in the Large Hadron Collider. If jets are indeed the sources of these particles, understanding jet acceleration mechanisms would help solve one of the longest-standing puzzles in high-energy astrophysics. The question of what determines whether a black hole produces jets is another frontier problem. Many supermassive black holes with substantial accretion disks show no evidence of significant jet activity, while others launch powerful jets. What distinguishes jet-producing black holes from their radio-quiet counterparts? The answer likely involves some combination of black hole spin, magnetic flux, and accretion rate, but the precise recipe remains elusive. Black hole spin is thought to be important because the Blandford-Znajek mechanism, which extracts energy from the black hole's rotation, is more efficient for rapidly spinning black holes. However, measuring black hole spin is extremely difficult, and the correlation between spin and jet power has not been firmly established observationally. Some theoretical work suggests that spin alone cannot explain the observed distribution of jet powers, and that magnetic flux may be equally or more important. The magnetic flux threading the black hole determines how effectively the Blandford-Znajek mechanism can operate. A black hole with abundant magnetic flux can launch more powerful jets than one with sparse flux, even if both have the same spin. The accumulation of magnetic flux on the black hole depends on the properties of the accretion flow and the history of the system, factors that are difficult to observe directly. Understanding how magnetic flux builds up and how it relates to jet power is an active area of research. The accretion rate also influences jet production, though the relationship is complex. At very low accretion rates, there may not be enough material to sustain a jet. At very high accretion rates, the accretion flow may become geometrically thick and may suppress jet formation through various mechanisms. The most powerful jets may be produced at intermediate accretion rates, where conditions are optimal for magnetic flux accumulation and energy extraction. However, the details of this relationship are still being worked out. The stability of jets over their enormous lengths is another puzzle. Jets maintain their coherent, collimated structure across distances of millions of light years, despite the many instabilities that could potentially disrupt them. How do jets remain stable over such vast distances? The magnetic field structure within jets likely plays a crucial role, providing a kind of electromagnetic backbone that resists disruption. However, the details of how magnetic fields maintain jet stability and under what conditions jets do become unstable are not fully understood. Observations show that some jets do become disrupted, breaking up into disconnected blobs or bending dramatically from their original direction. Understanding what triggers these disruptions and how they affect jet evolution is important for understanding the diversity of jet morphologies and the efficiency of jet feedback. Numerical simulations have begun to explore jet stability, but the computational demands of simulating jets over their full range of scales remain challenging. The connection between jets and other forms of black hole outflows is another area of active investigation. In addition to relativistic jets, active galactic nuclei can produce slower, wider angle outflows, known as winds. These winds may carry significant amounts of mass and energy, and may contribute to feedback alongside or instead of jets. The relationship between jets and winds, whether they are distinct phenomena or different manifestations of the same underlying process, is not fully clear. Some theoretical models suggest that jets and winds represent different modes of black hole activity, with jets dominating at low accretion rates and winds dominating at high accretion rates. Other models suggest that jets and winds can coexist, with the jet occupying the polar regions and the wind filling the equatorial regions. Observations of individual sources sometimes show evidence for both jets and winds, supporting the coexistence picture, but the overall relationship remains a subject of debate. The role of jets in the early universe is another frontier topic. Observations indicate that powerful jets existed when the universe was less than 1 billion years old, implying that supermassive black holes and their jets formed remarkably quickly after the Big Bang. How did these early jets form, and what role did they play in the evolution of the first galaxies? These questions connect jet physics to cosmology and the study of the early universe. Early jets may have been particularly important for distributing energy and magnetic fields through the young universe, influencing the formation of subsequent generations of galaxies. The first jets may have looked quite different from jets today, forming in environments with different gas densities, metallicities, and magnetic field strengths. Understanding early jets requires both observations of distant sources and theoretical models that can extrapolate current understanding to the conditions of the early universe. As we survey the unanswered questions in jet physics, we see a field that is vibrant and active, with many opportunities for discovery. Each question represents a frontier where current understanding meets the unknown, where new observations and new ideas can make significant contributions. The history of jet research shows that progress often comes from unexpected directions, with new telescopes revealing phenomena that were not anticipated and new theoretical insights reframing old problems in productive ways. The questions we have discussed are not merely academic puzzles. They connect to broader issues in astrophysics and physics, from the nature of space-time near black holes to the evolution of galaxies and the origin of cosmic rays. Answering these questions will deepen our understanding not just of jets, but of the universe as a whole. The frontier of jet research is a frontier of human knowledge, where curiosity and ingenuity continue to push back the boundaries of the unknown.